Good day, Justin Millwright, College of Physics here, and welcome back. What are we going to do today? Or now, in this segment, we are going to further investigate motion of objects, right? So we've looked at the definition of acceleration and velocity based upon time derivatives of displacement, or position, I should say. And now I just want to employ that to a little bit of a greater degree here with a nice little problem. So this problem is going to be split up into a few different parts because it can get pretty long here really quick. So the first part is going to deal with averages, and then we'll start to get into instantaneous values. So here's the first part of the problem. All right, so what do we have? We've got ourselves an expression that models the behavior of some object moving in one dimension, which we're going to say is the x dimension. And we got a function that says that x of t is equal to negative 1/2 t cubed plus 3t squared. So there's a nice representation. Of course, this 1/2 and this 3 have to have some proper SI units. Not going to worry about that right now. They do, such that when we evaluate this at some time, we get meters. SI units, good. So what do we want to do with this? Well, first off, we want to know what is the average velocity between t equals 0 and t equals 3 seconds. So part A, we want the average between t equals 0 and t is equal to 3 seconds. All right, so what do we need? Well, again, we note that the average velocity, again, we're just dealing with one dimension, so I'm leaving off the little vector sign here. The average velocity is going to be delta x over delta t. So we need to know what delta x is. Delta t is pretty easy, that's just 3 seconds. So delta x is going to be our x final minus x initial, and this will be divided by t final minus t initial, of course. So then we need our x final and our x initial. Well, x final is going to be x of t evaluated at t equals 3 seconds. So x of t is equal to 3 seconds. Oops. Is x final minus x of t is equal to 0 divided by 3 seconds minus 30 seconds. So this is what that kind of spells out into. And then, of course, we need x of t equals 3 and x of t equals 0. So x of t is equal to 3 seconds is equal to negative 1/2 times 3 seconds quantity cubed plus 3 times 3 seconds quantity squared. And what do we got? 27 halves and 27, so we should get 27 halves. Let me just make sure here. We got 3 cubed minus cubed, yeah. 27 halves grand, we got 13.5 meters. So there's the position of the object at t equals 3 seconds. Where was it at t equals 0? Well, we just go ahead and look. We evaluate this at t equals 0. Well, t equals 0, that gives us 0. So we're starting at the 0 meter mark, moving to the 13.5 meter mark, and thus we'll have the average velocity over that time interval from 0 to 3 seconds is going to be equal to 13.5 meters minus 0 divided by 3 minus 0, which is just 3 seconds. And let's just stick it in here real quick. 4.5. We got ourselves 4.50 meters per second. So over the first 3 seconds, okay, the average velocity of the object is 4.5 meters per second. In order to go from 0 to 13.5 meters away in 3 seconds, it would have to travel at an average rate of 4.50 meters per second. Does that mean that's how fast it's going the whole time? And the answer to that is probably not. But that's yet to be seen. So there was a part A. Part B, we do the same thing, but instead of saying t equals 0 to t equals 3, we'll look at the average between t equals 2 seconds and t is equal to 3 seconds. So we've got the same formalization here. We've got the v average is going to be delta x over delta t. which is going to be x of t is equal to 3 seconds minus x of t is equal to 2 seconds divided by 3 seconds minus 2 seconds. So what do we need? Well, we've already got x of t equals 3 seconds. That's 13.5. Let's just get x of t equals 2 seconds. X of t is equal to 2 seconds is equal to -1/2 times the quantity of 2 seconds cubed, which just gives us -4 there, plus 3 times 2 seconds squared. So we've got 12 minus 4, right, 8. 8, 4 minus 4 times 3 is 12. 12 minus 4 is 8 meter mark. So there we go. We can go ahead. I'm just going to stick it in up here because now we know we got 13.5 meters minus 8 meters divided by 1 second. So what does that give us? Well, that looks like that's going to be about 5.5 meters per second. So the very fact that over the first 3 seconds we got 4.5 meters per second, and over a 1 second time interval between 2 and 3 seconds, got 5.5, we're not getting the same average value everywhere, so that tells us that the velocity has to be changing. If we were moving at a constant rate over that entire time interval, then we would get the same average values. Averages and constants are defined the same way. But we're not, so there is a variation in the velocity. So let's do this one more time. And we'll look now between t equals 2.99 seconds and t is equal to 3 seconds. So again, shrinking the time interval down, approaching the instantaneous value. See what we get here. The average between t is equal to 2.99 seconds and t is equal to 3 seconds. So following from all of this, we need ourselves, what is t of x of t is equal to 2.99 seconds. And that's going to be -1/2 times 2.99 seconds cubed plus 3 times 2.99 seconds squared. And that, calculator for here, we got -0.5 times 2.99 cubed plus 3 times 2.99. All right. Whew. I get something around here. Yes, I did. Go back to the entry. And that would be squared. 13.45485. 13.45485 meters. Well, that's really close to 13.5. But again, we're looking at t equals 2.99 seconds. At t is equal to 3 seconds, 1/100th of a second later, we're at 13.5. So what do we have with this? Well, we've got delta x is going to be equal to 13.5 minus 13.4545 meters equal to 13.5 minus the answer gives us 0.041495. 0.045, excuse me, 0.0451495 meters. So in that 1/100th of a second, this object has moved this amount, this distance, which is, what, 4.5 centimeters or so, a little bit over 4.5 centimeters. All right, so then we want to go ahead and get what v average is. And v average is going to be delta x over delta t, which will then be 0.0451495 meters divided by 0.01 seconds, which is then equal to 4.51495 meters per second. And we can round that off and call it 4.51 meters per second, 3 significant figures, but I'll leave them all out there, and there we go. Well, that's not how fast it's actually going. That's still just an average velocity over a very small time interval. So, nonetheless, we can shrink down time intervals and start to approach the instantaneous velocity. So now this transitions into part 2 of this problem. So, yeah, let me erase this up and then we'll start part 2. So one second. All right, so looking at part 2 of this problem, Yeah, let's just do it. Here it is. All right, so we've got the same function describing the same object, and what we want to know is things like, hey, what about the instantaneous velocity? What about time extents over which things particularly change or mirror some other aspects? So let us just start with this. Again, we've got ourselves that x of t is equal to negative 1/2 times t cubed plus 3t squared. Great. And at part A, we are asked, what is the instantaneous velocity at t equals 3 seconds? V evaluated at t equals 3 seconds equals what? Well, in order to get the true value of the velocity at a particular moment in time, we note that the velocity is the first time derivative of position. And here's the function that describes position. So what do? We take the time derivative of it. d by dt of our negative 1/2 times t cubed plus 3t squared. So take the time derivative of that. That is pretty easy here with a nice polynomial here. We've got negative 3/2 t squared plus 6t. So this here, this is now v of t. This is the function that describes the object's velocity throughout time. So we've got v of t is equal to negative 3/2 t squared plus 6t. Definitely not constant, right? It varies quadratically. So what's that? Doesn't answer the question yet, but we need this function in order to answer this. Really, we could use this to say what's the velocity at any given moment in time. It doesn't matter. But we asked for a specific one. So we'll look then at v of t is equal to 3 seconds. It's going to be equal to negative 3/2 times 3 seconds quantity squared plus 6 times 3 seconds. There we go. And what do we got? 18. Let's just do this. 1.5. Negative 1.5 times 9 plus 2. We got 4.50. That's odd. 4.50 meters per second. So it turns out that at t is equal to 3 seconds, the object's velocity is 4.50 meters per second. That's pretty neat. But what did we get when we evaluated the average value between 2.99 and 3 seconds? We got like 4.51495, so on. We got some extra figures there. We didn't get exactly that. We were really close to it. Nonetheless, this is the instantaneous velocity at t is equal to 3 seconds. We wanted it at t equals 2 seconds. Evaluate that at t equals 2. Want it at t equals 0 seconds? Well, that's easy. The object was at rest at t equals 0. 0, 0, 0. All right, so then we've got ourselves a little bit of a part B here. What time is the object's velocity equal to 0? When is v equal to 0? All right, well, that's a good question, right? Of course it is. So we want this to be equal to 0, and we'll figure out what time that occurs at. So can we do that? And the answer is, yeah, we already know 1, but let's find all of the times at which it's equal to 0. So we have that v of t is equal to this, and we need v of t to be equal to 0. So 0 must be equal to negative 3/2 t squared plus 6t. There's the velocity that we want, and what can we do with this? Well, we can solve it out, right? We can factor out a t out of there and say that 0 is equal to t multiplied by negative 3/2 t plus 6. And what do we get out of that? We get 2 solutions. One of the solutions is v is equal to 0 at t is equal to 0. If t is equal to 0, 0 times whatever this is equal to 0. So there's one solution. The other solution comes from this. If this term here is equal to 0, 0 times whatever we have for this is equal to 0 as well. So we've got ourselves that negative 3/2 t plus 6 is equal to 0 will give us the other solution. We can solve that out, and what do we get? 12/3. So we've got ourselves t, negative 6 times 2 divided by 3. Negative 3 gives us t is equal to 4.00 seconds. So those are the two solutions. Two instances at which time the velocity of the object is truly 0. When it starts and at t equals 4 seconds. So that's great. I got another question here, and I got to reference this because there's so many things that this is asking. I got it written down here. At what time is the instantaneous velocity equal to the average velocity between t is equal to 0 and t is equal to 3 seconds? So when is v equal to v average as calculated between t is equal to 0 and t is equal to 3 seconds. So we want to know, when's the instantaneous velocity equal to the average velocity when the average velocity is calculated between this time interval right here. So we've already done what the average velocity is between that time interval in the preceding portion of this. And this will make things a little bit easy on us, but we'll still kind of work through this and see what's going on. We know that v average between the t equals 0 and t is equal to 3 seconds is the negative 13, excuse me, not negative, it's the 13.5 divided by 3, which gave us 4.5 meters per second. Well, that is the average velocity as calculated between t is equal to 0 and t is equal to 3 seconds. We want to know, is there a time between t is equal to 0 and t is equal to 3 seconds that the instantaneous velocity is also equal to that? Well, we know at t equals 4 seconds it's equal to 0, and it starts at 4.5, excuse me, it doesn't start at 4.5, it goes to 0 and goes up to 4.5 at t equals 3 seconds. Well, that kind of tells you it right there, but nonetheless, let's calculate this out, right? So we want the instantaneous to be equal to this. So 4.5 meters per second is equal to, well, here's the function that describes the instantaneous velocity. So we've got ourselves negative 3/2 t squared plus 6t. So we've got that going on for us. And what do we get out of this? Well, we can't just factor out a t. We'd have to complete the square or ultimately use a quadratic formula for this. That would be the best thing to go about. So we could rewrite this in standard form, negative 3/2 t squared plus 6t minus 4.5 is equal to 0. We've got an a term, a b term, and a c term. So we've got the a is equal to negative 3/2, b is equal to 6, and c would be equal to negative 4.5 in utilizing the quadratic formula. So we quadratic solve this out. Maybe you have it programmed, and maybe you don't. Hopefully I do right now to expedite things, but we've got negative 1.5, we've got a 6, and we've got a negative 4.5. Grand. And what do I get out of this? I get 2 different times because, well, it's quadratic. And both happen to be positive, which is good. None of it's imaginary, which is good, which means that there's 2 physical times at which the object's velocity, true velocity, is equal to 4.5 seconds, 4.5 meters per second, which happens to be the average velocity between t equals 0 and t equals 3 seconds. So if we solve this out, and we get ourselves that t is equal to 1 second, and t is equal to 3 seconds. So if we already knew at t equals 3, the instantaneous velocity was 4.5, we retrieve it here, but there's another time. T is equal to 1 second. And that is something that we didn't have. We had to solve it out. So little things like that to kind of pay attention to in a sense. And that was a part C there, right? Whew. Yeah. This one's C. All right, let's move on to a part T, part D, not part T, but part D. What's the position of the object at that time? So D. What is x at the time at which the instantaneous velocity is equal to the average? So there's two different times at which that occurs, t equals 1 and t equals 3. So really this is asking what is x at t is equal to 1 and t is equal to 3 seconds. We already know, we've already evaluated it, x of t is equal to 3 seconds was equal to our 13.5 meters. So 13.5 meter mark, the object's going 4.5 meters per second, which is equivalent to the average value between 0 and 3 seconds. We've also got x of t is equal to 1 second, which is then equal to -1/2 times 1 second cubed plus 3 times 1 second squared. So what do we got? We've got 3 minus 1/2 is equal to 2.5 meters. So at the 2.5 meter mark and the 13.5 meter mark, the object is going 4.5 meters per second. There we go. That one was pretty easy to get. And we move on to a couple more little questions here. At what time is the object's average velocity equal to 0? There's a good question. E. When is the average equal to 0? And this is between t is equal to 0 and t is equal to 6 seconds, starting at t equals 0. So, what do we have? Well, we've got x of t is equal to 0. Oops, sorry about that. X of t is equal to 0 is equal to, well, we've already said it, it's equal to 0. We start at the 0 meter mark. And what do we want? We want that v average is equal to 0. Well, how do we calculate v average? V average, again, is equal to delta x over delta t. So what does this really mean? That we want the average value to be equal to 0? What time does that occur at? Well, that means delta x must be equal to 0 if the average value is going to be equal to 0. So we need to know at what time is the displacement that this object has undergone equal to 0. That is, when is it back to where it started at? Sometime between t is equal to 0 and t is equal to 6 seconds. Well, let's see. We've got that delta x, again, is going to be some x final minus x initial, which is going to be some x of t that we're trying to find minus 0, because x initial is equal to 0 because we're starting at t equals 0. So it really comes out to say, hey, when is x of t equal to 0? Besides at t is equal to 0. What other time? So again, we got that x of t is equal to -1/2 t cubed plus 3t squared. And saying that that has to be equal to 0. We can factor out 2 factors of t here, t squared really. So we've got that 0 is equal to t squared multiplied by -1/2 t plus 3. There we go, factored out that t squared, that gives us 0. And that's one of the times, and the other times in here. This is equal to 0, this times t is equal to 0. So we've got that -1/2 t plus 3 is equal to 0, which gives us t is equal to 6 seconds. So at t is equal to 6 seconds, we have that the average velocity of the object will be equal to 0 as calculated from t equals 0 to t equals 6 seconds. Ultimately, the object's back to where it started from. That's what we've got. So, it's a cool little thing there. Just kind of read into the words. What is this really asking me? Average velocity equals 0. What does that mean? that means that the displacement must be equal to 0. So that's the key with that, is making that connection there. All right, a couple more little pieces. What is the instantaneous velocity when the object is at the 10-meter mark? Oh, this is a good one. What is this? Part F or something? F. What is V equal to when X is equal to 10 meters? And we'll say the first time here, because there could possibly be more than one time that it's at the 10-meter mark if this object comes back to where it started, right? So let us just constrain it to the first time. So what do we need to do? Well, we just go like this and say, well, let's see. We've got that x of t is going to be equal to 10. So x of t is equal to 10, which we know is equal to negative 1/2 t cubed plus 3t squared. And well, why do we need to consider this? Because we need to figure out at what time it's actually at the 10-meter mark so that we can evaluate the velocity at that moment in time. That's what we need to do. Again, the question is asking, what is the object's velocity when the object is at the 10-meter mark, the first time? So we need to figure out the first time that it's at the 10-meter mark. So how are we going to solve this out? Factor something out here. You could factor out a t squared on this side, but that's not going to do us much good, actually, because this isn't 0 here. This is a numeric value. So what are we going to do? Well, we could go like this and say we got the negative 1/2 t cubed plus 3t squared minus 10 is equal to 0. Does that help us? It does, in a sense. It helps us see that this is going to be trouble. Why? Because this is cubic, it's not quadratic. You can't use a quadratic formula on something that's cubic. You could use the cubic formula on it. Anybody seen the cubic formula before? If not, look it up. Look it up. It's not the prettiest, actually it's quite elegant, but it's not that easy to utilize. It's pretty big, there's lots of different steps with it, lots of testing numeric values, and we're not going to use it. We're not going to use it, but I do encourage you to look it up, just to kind of see it and say, oh my gosh, there is a cubic formula. Mathematicians have developed it. But we need to figure this out. How can we figure this out without using the cubic formula? Well, at very least, we could narrow things down. We could start to get an idea of the time at which that occurs at. A couple different ways that we could do this. We could do it graphically. If we had a computer that would graph this out, we could go along the graphical representation of it and see that there's a point in time at which the displacement of the object or position of the object is the 10-meter mark. And we can extract that time off the graph, and boom, done. Evaluate V at that time, and we're good. If you don't have a nice graphing system that allows you to do that, then you're almost forced, in a sense, to use numerical analysis. And that is try different values, see what's going on, see if you can figure it out. Well, we know this. We know that at t is equal to 0, we're at the 0-meter mark, and at t is equal to 3, we're at the 13.5-meter mark. So the first time that it happens should stand to reason that it's somewhere between t is equal to 0 and t is equal to 3 seconds. So at least we've got a little window here, a little window of possibility. We have that t should be greater than 0 and should be less than 3 seconds, just by what we already know about the system. And this is where it does come into play, understanding what all these quantities mean, not just making numbers out of them. They have physical aspects that you're going to want to understand and know. So we're in between these times. What can we do with this? Well, we can start testing stuff out and say, hey, let's look. Look at t is equal to 2 seconds. How are we going to look? Well, the easiest way to look is stick this into your calculator and evaluate it, right? if at t is equal to 2 seconds, this whole thing adds up to be equal to 0, hey, 2 seconds is a solution for it. If it doesn't add up to be 0, then we've got to figure out, do we need to look at a different time? What's the different time that we need to look at? So it's almost easier, in my opinion, to keep this in the form that we originally had, which was this form right here. Instead of sticking this all in your calculator, you just stick this in. So I'm going to go ahead and do this. So check this out. I got negative 0.5 times, I'm going to put 2.00 cubed plus 3 times 2.00. And I'm going to enter that in, and that says, oh, 2. At t is equal to 2 seconds, you're at the 2 meter mark. Well, that's not going to do it, right? So now I can go and recall that entry and say, you know what, how about the 1 second? So I'll change the 2 to a 1 and say, well, now you're at the 2.5 meter mark. At t is equal to 1 second. Put something in here wrong. 3 times, yes I did. So hold on a second here. Entry, I didn't square the last term. I was wondering why that was coming out awkwardly. So 2, so let me go back to 2, sorry about that. Evaluated at t equals 2 seconds, we get 8. X is equal to 8 meters. That's pretty close to 10, right? Well, if we went back down to 1, we're at the 2.5 meter mark, so 1's not going to do it. So let's look a little bit higher up here and say, what about 2.5? So I'll stick this back in, recall the entry, and change the 2.00 to 2.50. Oops. 50. And now I get at 2.50 seconds, x is equal to 10.9375 meters. Uh-oh, that's too far. We don't want it to have gone over 10, we want it to be at 10, so it has to be somewhere between 2 and 2.5 seconds. So this is what you end up doing, narrowing it down until you have it sufficiently nailed down there. And that's dependent on how many significant figures or what level of precision you want it to. Generally for us, we look for 3 significant figures. Get the 3 significant figures, we're good. So I could go ahead and say, what about like a 2.25? And just keep on doing this. And yeah, does it get a little boring? Sure, but it's kind of neat to be able to do. 2.25 gives us 9.49, so it's got to be greater than 2.25. So now, again, we've narrowed it down to sometime between 2.25 seconds and 2.50 seconds. So we do this again, 2.35 we'll try. Why not? 2.35, we got 10.078. That's pretty close. It's a little bit too much, so maybe we try 2.32. 2.32, 2.32. And now I got 9.90, so that's a little bit too little. And now we've got it narrowed down, sometime between 2.32 seconds and 2.35 seconds. So if we kind of get the idea here, this is just, again, kind of going through things. I put in the 2.34, and I got 10.02. Within reason, we can say that t is approximately 2.34 seconds. Generally, we'd want maybe one more significant figure, but at that, x is equal to 10.02 meters. So now we'll come to play where we actually evaluate the velocity at that time to say how fast is it going when it's at the 10 meter mark the first time. So v of t is equal to 2.34 seconds is equal to, well, we've got v of t, did I just erase it? That's okay. We've got v of t is equal to -3/2 times t squared, which is 2.34 seconds, quantity squared, plus 6 times t. T again is 2.34 seconds. And what do we get out of this? Dun, dun, dun. -1.5 times 4 squared plus 6 times 2.34. And I get about 5.8266, we'll call it 5.83 meters per second. 5.83 meters per second when it's at the 10 meter mark. And this again is approximately because this is the approximate time at which it's at the 10 meter mark. It's a little bit less than that. It's probably like 2.38 something. But nonetheless, there we go. We answered that up and we figure it out. That's what we do, figure stuff out. But it comes with understanding what the question is asking and what pertains to solving stuff out. All right, so there's one more part with this. I'm gonna erase this board off and then we'll go ahead and do that last part. All right. All right, so here we go with part 3 of this problem. And let's just take a look at part 3 here, dealing with the acceleration now. All right, so we've got ourselves the same function again. It describes the variation of the object's position with respect to time, -1/2 t cubed plus 3t squared. We have already determined that, let me do this, that the velocity as a function of time, v of t is equal to dx by dt, which was equal to -3/2 t squared plus 6t. And now we're asked about the acceleration, like what's the average acceleration between t equals 0 and t equals 3, between t equals 2 and t equals 3, and 2.99 and 3. So we're doing the same thing with sort of shrinking down time intervals, looking at average acceleration. So we start with this. A average is equal to delta v over delta t. That's how we compute an average acceleration. What we got to be aware of is this delta v includes instantaneous values, right? We've got a v final minus v initial divided by t final minus t initial in general. So it is important that we note that these velocities are instantaneous velocities at those time intervals which we're trying to calculate what the average velocity is. So we want the average velocity between t is equal to 0 and t is equal to 3. A average between t is equal to 0 and t is equal to 3 seconds. Well, what do we need? We need v of t is equal to 3 minus v of t is equal to 0 divided by 3 seconds minus 0 seconds. These are seconds there, seconds. So there it is. This is going to be our A average there. We know the time interval, great. It's just a matter of getting what is the velocities here. So at t is equal to 3 seconds, we had 4.5 meters per second, right? 18 minus 27 halves minus 13.5. 18, 13.5, 4.5. So we had ourselves that this is going to be 4.5 meters per second minus, we evaluate this at t is equal to 0, and that is 0 meters per second, and that's going to be divided by 3, and that gives us a whopping 1.5 meters per second squared. So there's the average acceleration between t is equal to 0, t is equal to 3 seconds. Let's do it again. So this was like part A, part B. Now between t is equal to 2 and t is equal to 3 seconds. So we've got ourselves A average is going to be v of t is equal to 3 minus v of t is equal to 2 divided by 3 seconds minus 2 seconds, seconds. That is going to be equal to, we've already discerned that at t is equal to 3 seconds, we have 4.5 meters per second. Then we evaluate this at t is equal to 2 seconds. V of t is equal to 2 seconds is equal to -3/2 times 2 seconds quantity squared plus 6 times 2 seconds. So we've got ourselves 12 minus 4, which was 8. 8 meters per second. So, is equal to 2. All right, 12. This is 4 times 3 is 12 minus 6. 6 meters per second. And that's something up here. Ba-doom, 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 ba-doom. Not going that fast then. Yeah, I've got something messed up here. 12 minus 1.5 times 4. 6 seconds. 6 meters per second, excuse me. And yeah, that's okay. That's okay. So we've got minus 6 meters per second divided by 1 second. Well, we have to recall something here. This object is at some point slowing down because well, it comes back to what its initial position was. We found that its velocity was equal to 0 at t is equal to 4 seconds. So at some point, yeah, it's speeding up and then it starts slowing down. As you can think of it, there's some inflection point. But nonetheless, this is what we've got here. And now we've got equals negative 1.5 divided by 1 meters per second seconds equal to negative 1.5 meters per second squared. So that's a vastly different quantity than we had for between t is equal to 0 and t is equal to 3. It's the same numeric value, but one's negative, one's positive. This is speeding up, this is slowing down. But these, again, are average values. You can see now we're doing between t is equal to 2.99 seconds and t is equal to 3 seconds. And what do we do with this? We're going to go ahead and calculate what is v of t is equal to 2.99 seconds. That is going to be negative 3 halves times 2.99 seconds quantity squared plus 6 times 2.99 seconds, which will give us 1.5 times 2.99 squared times 6 times 2.99. Negative 1.5 times 2.99 squared plus 6 times 2.99. There we go. Now we've got ourselves 4.52985 meters per second at t is equal to 2.99 seconds. And then we can go ahead and compute what the average acceleration is. That is going to be equal to the final, which is 4.5 meters per second, minus the initial at t is equal to 2.99, 4.52985 meters per second. That's a 4 there. That is going to be divided by 0.01 seconds. So we'll just do that. Minus 4.5. That is going to give us that the average acceleration over that time interval is negative 2.985. 2.985 meters per second squared. All right, so definitely slowing down right around t is equal to 3 seconds, right? So the question is, what is its actual instantaneous acceleration at t is equal to 3 seconds? A, B, C, D. A is equal to, well, A is equal to dv by dt, which is equal to d squared x by dt squared. We've already got what dv dt is, excuse me, what v is, so we can write that A is equal to d by dt of negative 3 halves t squared plus 6 t, like this. And what do we get ourselves there? We're going to get ourselves negative 6 halves, which is going to be negative 3. Negative 3t plus a 6. So there's the function that describes the acceleration with respect to time. And then we just evaluate it. At t is equal to 3 seconds, a, t is equal to 3 seconds, is equal to negative 3 times 3 seconds plus 6, which is A is equal to negative 3 meters per second squared. we go really close to what we calculated for the average value over that 1/100th second of a time interval. But there is the true actual acceleration at t is equal to 3 seconds. And really, again, we can get it at any moment in time based upon this function right here, which was ultimately gotten by one thing. All of this was gotten by knowing one thing at the very beginning for all the parts. The x of t was equal to -1/2 t cubed plus 3t squared. Everything else was solved by knowing the function that describes the position of the object with respect to time. Pretty powerful, right? Knowing this. Everything else is extractable from that. Along with, of course, the definitions of velocity acceleration. All right, I think there may have been one point in part B where I said at t is equal to 2, the velocity was 8 meters per second, and it turns out to be 6. That was me going a little too fast, but I think that's fairly insignificant. And yeah, that's basically that. Whew, that was a long one. I agree. Keep on going though. Accelerating into the future. Take care.